let's take a look at this function series. You can see that all the functions are defined everywhere on the number line. This means that we don't have any bad points on this line. Now let's talk about convergence, and for that we will use the ratio test. So let's calculate this fraction. We have fn plus 1 over fn. And to make our lives easier, we can rewrite this as fn plus 1 times 1 over fn. And let's calculate this. So fn plus 1 means that here, instead of n, we have to write n plus 1. We have n plus 1 over n plus 1 squared minus 3 times x plus 2 to the power n. And this is the reciprocal of the general term. So we have n squared minus 3 over n. And we also have 1 over x plus 2 to the power n minus n. Now let's combine similar terms. We have n plus 1 over n times n squared minus 3 over n plus 1 squared minus 3 times x plus 2 to the power n over x plus 2 to the power n minus 1. And we can further rewrite this as 1 plus 1 over n over 1 times 1 minus 3 over n squared over 1 plus 1 over n squared minus 3 over n squared. And the last one will be x plus 2. And now rho will be the absolute value, the limit of the absolute value of this fraction. So rho will be limit n goes to infinity, absolute value of fn plus 1 over fn. And to see this limit, we have that n goes to infinity, so 1 over n goes to 0, 3 over n squared also goes to 0, and here 3 over n squared also goes to 0, and here 1 over n goes to 0. Therefore, this limit is x plus 2 in absolute value. Now the test tells us that we need to investigate the case when x plus 2 in absolute value is smaller than 1, and these will be the points where the series is absolutely convergent. So let's see where these points are. So x plus 2 in absolute value is smaller than 0. This means that the distance from minus 2 is less than 1. So this will be from minus 3 to minus 1. In this interval, distance is less than 1 from minus 2. And let's mark these points also on this number line. So here we have minus 3, and here we have minus 1. And between these points, we know that our function series is absolutely convergent. The next step is to investigate the case when x plus 2 in absolute value is greater than 1. So the test tells us that these are the points where the function series is divergent. And if you take a closer look, this will be the outside of the previous interval. So we have the interval from minus 3 to minus 1, and we just take the points outside of this interval. And if we also mark these points on the number line, we have to mark from minus infinity to minus 3 and from minus 1 to plus infinity. And from the test, we know that at these points, the function series is divergent. Now we have only one case left, when that case is when rho is 1. So when rho is 1, then x plus 2 in absolute value is 1, and this means that x could be minus 3, or x could also be minus 1. If x is minus 3, then we have to write minus 3 here instead of x. So we have this series, we have n over n squared minus 3 times minus 1 to the power n minus 1. And if x is minus 1, we have to write minus 1 here instead of x. And minus 1 plus 2 is 1, and 1 to any power is also 1. So we just have to write down that we have a series when we have n over n squared minus 3. And here these are number series, we are no longer talking about function series. And as you can see, this is an alternating series, and this is the absolute value of the alternating series. And that's the reason why we will take a closer look at this one first. So you know that this is similar to previously studied series where we have 1 over n, and from previous studies we also know that this is a divergent series, and because this is a divergent series we know that this must also be a divergent series. And since this is a divergent series, we know that this other series could not be absolutely convergent. But you know, it could be conditionally convergent, and for that we need to check two conditions. The first condition is that we must have that the limit of n over n squared minus 3 must be 0, and you know, if you take a closer look at this one, you can clearly see that this does indeed go to 0. So the first condition holds, and the second condition states that this must be a decreasing sequence. To check that, we differentiate. So let's take the derivative of x over x squared minus 3, and you just use the quotient rule. We have x squared minus 3 minus x times 2x over x squared minus 3 squared. Let's try to combine the terms in the numerator. So this will be minus x squared minus 3 over x minus 3 squared. And obviously the denominator will always be positive, and the numerator is always negative. So we have negative over positive, which is negative. And this means that the derivative is negative, so this function is decreasing, and because this function is decreasing, this sequence of numbers also decreasing. So the second condition also holds, and this means that it is conditionally convergent. So at minus 3 we have that the function series is conditionally convergent, and at minus 1 we have that the function series is divergent.